Hi, this is Professor Wyatrowski, and I'm here to go over the answers to the genetics quiz that you took today in class, and so that you can check and see how you did on your quiz. The first question says, let P equal purple flowers and P equal white flowers. And T equals tall plants and little t is dwarf. What would be the appearance of a plant with the genotype big P, little p, big T, little t? Well, we know that big P is purple and we know that big T is tall. So although they're heterozygote for both characteristics, they would be purple and tall. Okay, question 2 tells us that, again, purple is big P, and that little p is white, and T is tall, big T is tall, and little t is dwarf. Says what combination of gametes could be produced by a heterozygote for both traits? So that means the individual looks like this. The gametes, again, we're going to use that algebraic FOILing method. So we're going to get a big P with a big T. We're going to get a big P with a little t. And then we're going to do the same thing with the little p's. We get little p and big T, little p and little t. Remember that these represent homologous pairs. This is a homologous pair, and this is a homologous pair. And in meiosis, the individual chromosomes have to split, so every gamete gets one of the two P genes, whether it's the big one or the little one, and each one gets the T allele, whether it's the big T or the little t. So we have to look at all the possible ways that the big P's and the little t's, or the P's, and the t's can combine. All right, for question 3, it tells us that we're going to be crossing these gametes from the above question, and it wants to know how many phenotypes would be white tall. So you run your Punnett square like we would normally in class. And I went ahead and set it up for you, and you would go ahead and cross each box as you would normally, and then you count how many are white and tall. And at the end, you should have come up with 3. Okay, so remember, this is a fairly traditional dihybrid cross. So you're going to expect to see the 9 to 3 to 3 to 1 ratio. So you know the answer is going to be 9, 3, or 1. 9 is usually the dominant characteristic, so that would have been purple and tall. And we want to know white tall. So we know that this would have been purple tall. And we know that the 1 would be completely recessive, so that would have been white short. And so we know that the other phenotypes must have been one of these. So you could have figured this out without having run the whole Punnett square. But if you wanted to do the whole Punnett square, you could have. And you should have come up with 3 as the answer. All right, for question 4, and I'm just going to let you know I'm at home, and I have kids, I have dogs, I have cats, and I have kids playing over from the neighbors, so it's kind of hectic here, so I might get constantly interrupted. All right, question 4 says, when Mendel crossed 2 purple flower pea plants with each other, he obtained a phenotypic ratio of 3 to 1. His results are consistent with which of the following sets of parents? Well, to get a 3 to 1 ratio in Mendelian genetics, it's always a heterozygous with a heterozygous. So the answer would have been E for number 4. For number 5, it says that Irene and William are having their first child. Irene knows that her blood type is A, but William does not know his blood type. However, William knows that his mother and father were B. Their first child is a boy, named Gregory, and Gregory has type O blood. Of course, Irene and William did not understand how this happened. You could explain to them using which of the following choices? Well, the only way that they could have possibly had O would be that Irene is heterozygous, so she contains the A allele and the O allele, and that if William is indeed B, then his genotype is probably this. Okay, so it's probably B, that Irene's genotype is AO and William's genotype is BO, thus Gregory expresses the phenotype of O. Alright, so number 6 says a secretor is a person who secretes their blood type antigens into body fluids and secretions such as saliva. By comparison, a non-secretor does not. A person's status of a secretor or non-secretor is independent of blood type. Consider the following inheritance patterns. Well, if you look at the inheritance patterns, that a secretor times a secretor always gives you a secretor. A non-secretor and a non-secretor always give you a non-secretor. And secretor and non-secretor always give you a secretor. So secretor is obviously dominant to non-secretor. There's nothing fancy going on here. It's just a really typical Mendelian inheritance pattern. So the best answer for 6 is C, autosomal dominant. Number 7, obviously there was not enough information to determine an answer, so the answer would have been B because we don't know what the genotypic ratio is of. In number 8, it says, in white tigers, the absence of fur pigmentation is caused by a recessive allele. This allele also causes the tigers to be cross-eyed. If two tigers heterozygous for this allele mate and produce offspring, what percentage can be expected to be white and or cross-eyed? So we know that in this question, we'll put P for pigmentation, and little p is albino, cross-eyed. And we have two heterozygous tigers crossed. And we want to know what percentage can be expected to be white and or cross-eyed. This is going to give us that traditional 3-to-1 ratio in Mendelian genetics. We work it out. That would be a normal pigmented, normal pigmented, normal pigmented. And then here we have white and then therefore cross-eyed, so 25% would be white, and the same would be cross-eyed, so that would be A as the answer. Number 9 says that, and let CY equal curly wings, and CY plus is wild type, so that's his normal wings. Now this problem is coded in a Morgan-like fashion, so this is chapter 15. In Drosophila, the CY allele behaves as a dominant mutation that produces curly wings in the heterozygous condition, but also behaves as a recessive lethal mutation. Flies homozygous for the CY allele die before reaching adulthood. So CY is a fatal combination. So it wants to know that if we crossed flies heterozygous for the CY allele, what phenotypes would you find in the F1 generation? So we get our gametes the same way. Same for this person. Okay. And then we cross them. Okay, that's fatal. Curly winged. Curly wing, normal. So the answer would be A, we'd have wild type, and then we'd have curly wings. So number 10 says if you crossed flies heterozygous for the CY allele, what surviving genotypes would you find? So it's the same question as this one, except this is asking you for the genotypes rather than the phenotypes. So the answer would be C. You would find CY+, and you would see CY and CY+. So you have these two phenotypes because this one is fatal, so they wouldn't survive. All right, number 11 says that let Y equal yellow, let little y equal green, big R equal round, and little r equal wrinkled. If you cross a big Y, big R, P with little y, little r, P's, all individuals of the F1 would be heterozygote. Okay. You then perform an F2 cross and get the expected 9:3, 3:1 ratio. Which of the following is the correct genotypic ratio for yellow round F2 individuals? Okay, so you want the genotypic ratio. So in this case, you would set it up normally, get your gametes. So your Punnett square should look like this. And after you work them out, you should end up with finding that one box is big Y, big R, big R. And then you should find 2/16, so that's 1/16. 2/16, big Y, big R, little r. And then 2/16, big Y, little r, little r. And then 4/16 heterozygote. So the answer is D. My system is a little slow, so it's not keeping up with my writing. But the answer to this one should have been D. So you just had to work it out and figure out which genotypic ratio you get that produce yellow round individuals. Okay. Number 12 says that achondroplasia is a common form of dwarfism caused by an autosomal dominant mutation. If a person with achondroplasia married and had children with a person of normal height, what is the probability that their first child and second child would have achondroplasia? So this one's wanting us to connect two pregnancies together. There's a 1/2 chance per pregnancy of producing an achondroplastic dwarf because the one parent, if it's the male or the female, it doesn't really matter. But if they have achondroplasia, and this is the achondroplasic gene, there's a 50% chance that this would end up in one of the gametes. And so there's a 50% chance of producing an offspring with achondroplasia. Over 2 pregnancies, it's 1/2 times 1/2, which equals 1/4, which is answer B. Number 13 says you are a herpetologist studying snapping turtles. You house turtles in an incubator at 22 degrees. After a period of time, you find that some new baby turtles have hatched. Interesting, all the baby turtles are male. Basically, what you would probably hypothesize is that sex determination is influenced by temperature, and that actually is the case with turtles. But you would need more data, obviously, so C would be your best answer. Number 14, if a female was a carrier for sex-linked color blindness, what percent of her male children would also be sex-linked colorblind? Well, if she's sex-linked and she's sex-linked carrier, so she has one normal X and one bad X, and 50% of her gametes are going to get the bad X. Okay. So that's 50%.